Hi, welcome back. In this chemistry lecture, we are going to be discussing some of the properties of ionic compounds and a little bit on ionic bonds as well. So, when you have, now normally atoms are electrochemically neutral. They have the same number of electrons and protons. Atoms only form ions, positive or negative ions, when they interact with other atoms during the formation of ionic bonds. There are some weird circumstances, like the sun has a stream of ionized particles coming off of it, but that's very different, extreme physical and chemical conditions. So the fact that one atom loses an electron, and then that electron is, I guess you could say, stolen by the other, making one positively charged, the other negatively charged, that attracts them together. They form an ionic bond. It's an electrostatic attraction between the two of them. So all ionic compounds have neutral charges. There are these things called polyatomic ions, which we will learn about in the future, but ionic compounds in general are totally neutral. So you take the salt compound, the salt ionic compound, the sodium loses its electron, it has a +1 charge. Chlorine takes that electron, it has a -1 charge. Well, +1 plus -1 is 0. So, totally neutral. Again, electrostatic forces. The ionic bond is the electrostatic force in this case. It's a very, very strong attraction. It's basically the strongest type of attraction between atoms, is the ionic bond. So formula units describe ionic substances, or substances that are formed out of ionic compounds, I should say. Sodium and chlorine will always bond together in a 1-to-1 ratio. Sodium gives chlorine its single valence electron. Chlorine has 7, so that gives it 8, satisfying our octet rule, filling up those s and p orbitals, giving it a noble gas electron configuration. So no matter how much sodium chloride you have, whether it's an enormous chunk or a single compound of it, it's always a 1-to-1 ratio. So the chemical formula tells you in the simplest ratio how many of each atom you have. So NaCl. That means for every single sodium atom, there's a single chlorine atom as well. And formula units basically do the same thing. It's the lowest whole number ratio of all the ions in an ionic compound. Now, in ionic compounds, a formula unit and the chemical formula are the same thing. In pretty much, I'm not aware of an instance where that's not the case. There probably are exceptions, but in general, they're the same thing. For molecules, that's very different. Molecules will be the subject of our next chapter. They'll show you what I mean. So here's a here's a model of sodium chloride, right? And there are dozens, I don't know exactly how many of each atom there are here, but we can simplify it down to just a 1-to-1 ratio. 1 sodium, 1 chlorine. As long as you have a single sodium chloride, that will be chemically and physically identical to a much larger collection of a bunch of sodium chloride compounds bonded together. That is not the case for molecules. So the chemical formula for glucose is C6H12O6. The formula unit for that, we can reduce that. So that would reduce down to CH2O. But when you start removing atoms from molecules, they become different molecules. So if we reduce glucose in half, C3H6O3, that's glyceraldehyde, which is a completely different substance. And if you simplify it all the way down to CH2O, well, that's formaldehyde, which is also a completely different substance. So, topic of this chapter is ions. Moving on. Now, most ionic compounds, unlike several molecules, which can be gases or liquids, ionic compounds, for the most part, are crystalline solid substances, meaning they form like regular crystalline patterns. I have, I'll show you. In nature, we call these minerals. So I have a little mineral collection right over there. So this is pyrite, fool's gold. I don't know if the camera will focus on it. That is naturally how it exists. So this has not been shaped by a machine or a person. It naturally just forms like that. Fool's gold is made of lead and sulfur atoms, I believe, bonded together, and they form these repeating cubic crystals. And that's what minerals are, and there are thousands of different minerals. The vast majority of all ionic compounds have very high melting temperatures. Again, unlike molecules, they can be gases or liquid at room temperature. So we have what's called a coordination number. When you study the atomic structure of these crystals, these ionic compounds, then you find that there's a specific lattice pattern behind the way in which the atoms are arranged. And it's always very geometric and orderly. If we go back to the molecules here, we can see that now every glucose molecule is shaped like that, but it's a very abstract shape. Whereas the sodium chloride, well, that's a geometric repeating shape, and that's why they form crystals. Molecules really don't do that. So for these coordination numbers, I'll just show you the examples. Every sodium atom, we can look, they are surrounded on 6 sides by chlorine. There's one on top, one on bottom, front, back, left, right. For cesium chloride, there are 8 chlorine atoms that surround it, and the angle of which they're orientated, I guess we would say, from the central sodium atom is different. So there end up being 8 of them all around. The funny thing about ionic compounds is if you dissolve them in water, they can actually conduct electricity. Salt water is extremely conductive. Now, this happens for kind of a funny reason. The water molecule is polar. It's a neutral molecule, but the electrons are distributed unevenly. So the oxygen side of your water molecule is actually very slightly negatively charged, and the hydrogen side of the water molecule is slightly positively charged. That allows water to be a really great solvent. It can break apart ionic compounds like salt. You pour salt in water, it just dissolves naturally. Whereas it would take a tremendous amount of heat, a huge amount of heat, to melt those sodium crystals and get the compound or get the atoms to separate from themselves. Water will break apart the ionic bonds between sodium and chlorine with virtually no energy at all because it's polar. Now, normally an electric current is generated by the flow of electrons, but in ionic solutions, it's actually the flow of the individually ionized particles. So for sodium chloride, for example, the sodium is positively charged, the chlorine is negatively charged, because they're ions. The chlorine steals the electron away from it. So water is totally neutral. Salt all by itself is electrochemically neutral, so there's no current. But when you dissolve it, the negatively charged chlorine atoms will flow in one direction, and the positively charged sodium atoms will flow in the opposite direction. Now, it's a really weak current, but it still exists. So you can go on YouTube, and people take wood and they'll brush it with really salty water, and then they'll clamp car jumper cable things to it, or hammer in a nail on 2 sides, and then they'll hook up a battery or something to it, and the electric current just sort of randomly, we call this a dendritic pattern, like a dendrite, and it ends up forming these really cool patterns. So if you want to be mesmerized and waste some time on YouTube, look up, I don't know exactly what to type in, salt water wood burning, I guess, would be what you type in. So that's it for ionic compounds. Next time we'll take a look at the structure of how metal atoms are held together. Thanks for watching.